covariant. It's the same for everyone. So what we have done so far is to go over with some detail over the derivation of Hawking radiation in this simplified model of collapse. We have made some approximations in our way, just in order to be able to do computations, explicit computations. And now I'm going to mention quickly some of the what I call generalizations. I will go relatively fast because I want to finish the chapter today if possible. But at least I want to mention what are the possible things. As I said, in Hawking radiation there are zillions of different things we can discuss, so we could just have a whole course of Hawking radiation, so I have to summarize somewhere. So let me talk, they are disconnected, so let me first talk about one of them, wave packets. We have already discussed this. You know what is the problem? The problem is that, for instance, let's focus in out modes. We have been using, for out modes, we have used a basis for out modes that behave as I to the I omega u out divided by all the factors and the spherical harmonic, etc. And I told you that this is inadequate both physically because that represents waves which are extended in the hole, in any hole Cauchy hypersurface. So they are like plane waves that are defined in the whole space, and that is quite unphysical because real quanta are localized in certain region.
What does that look?
Inadequate is inadequate. That was with Q with C.
Q.
Q. Thank you. It was not tough enough. Physically and mathematically. Mathematically is not really a basis of our space of solution because it has infinite norm. Remember, the norm of these guys is proportional to the delta function omega minus omega prime, so that has indefinite norm. So mathematically, it's not a well-defined basis. And so, the argument was that we use it because it's very easy to manipulate, but in order to make it rigorous, what we have to do is to replace this basis by a basis made of wave packets. So a more convenient, I don't know why I'm writing in blue, I always want to write in black. A more convenient basis is made the same for the int and for the in basis. I am just focusing in one of them, but the same analysis repeats for the three of them. A more convenient basis is made of wave packets. There are many ways of writing wave packets. Let me give you one explicit construction of wave packets that was used by Hawking in his paper. And a possible choice is the following. The out modes, now for wave packets, they have four indices. Lm as before, but now I am replacing omega by j. So j is going to play the role of omega, of the frequency. And in addition to that, there is a capital T, which will play the role of at which time they are, or in which region of space-time they are localized. And the explicit expression, or possible one, is just take the previous out modes and do an integral in omega in some compact range, so from j epsilon to j plus 1 epsilon. And you can put here some smoothing factor, which Hawking choose 2 I 2 pi omega t over epsilon. This is a good choice of wave packets. So what we are doing is we are smearing the out mode that we had before on a compact range of frequencies, and that compact range of frequencies goes from j epsilon to j plus 1 epsilon. Where both j is forced to be positive or 0, and t both are integer numbers. And epsilon is a parameter that we choose much smaller than 1, and real, of course. So this is what a wave packet is. There's a smearing of the anormalized modes on a finite range of frequency. And you know, if epsilon is small enough, the frequency, these guys have contributions from different frequencies, but in a very narrow interval. Because if epsilon is very small, there is very little difference between this and this. So, in addition, these wave packets are, you can check easily that they are supported in a narrow range of U out, center in 2 pi t over epsilon with width of the order of 2 pi epsilon. Remember that the previous wave packets, the previous modes, out modes, they were defined in the whole U. This is U out that runs in straight class. They were defined everywhere. These guys are localized in some region. And this is the value of the center, and the width is inversely proportional to epsilon. And note that the range of frequencies in which the width in frequency is proportional to epsilon. The width in time is inversely proportional to epsilon, 1 over epsilon, as we may expect from the energy time uncertainty relation. If you have very definite frequency, they are really spread. In fact, these initial out modes, they just have a single frequency, so they are completely spread in U. Here we are dividing the uncertainty in frequency and in time. And they are normalized modes, so if you take these wave packets for all values of the parameters, they form a orthonormal basis of out of positive norm, positive frequency modes. Remember, I call positive frequency, but what I mean is positive norm modes with support in a straight class. the statement here is that you can do the same for the int and the in modes, just doing exactly the same with them. And therefore you have a well-defined basis for each of them. The norm of these modes is 1, it's not the delta, the Dirac delta. And you can repeat the computation of the volume of coefficients. It's exactly the same, except that you have 2 of these intervals in front of them, but it's just a matter of doing them more carefully, and the Hawking radiation you get exactly the same. But now much more rigorously, because you can talk about modes reaching Scrape class at late times, and that makes sense, because before that was not. So you don't write it, but the statement here is that A, you can do the same for the in and int modes. So have well-defined basis for all the focus spaces we have in our problem. And B, repeat the computation of the volume of coefficients, which is identical, except that you have these intervals in frequency in the middle. But after doing that, the result is exactly the same. With the only difference is that now it's much more rigorous, and it makes sense to talk about modes reaching Scrape class at late times, and that we couldn't because a plane wave is defined everywhere.
Is that for all frequencies or over particular frequencies?
So you can have modes reaching a Scrape class at late times for all frequencies you want, because this is for large T. If you choose T be large, the mode is getting here at late values of U, because remember U is just proportional to T.
Right, I know. I was just wondering if there was any correlation between J and T.
Between what?
J and T.
No, you can choose them, and omega you can choose them. So with J, so you can have modes here with any frequency that you want.
Okay.
I was going to say that. I was going to finish. So you can choose freely T and omega. They are not correlated.
What is that?
The width is correlated. The width in omega is correlated with the spread in time, as you may expect. Say.
What is epsilon?
Epsilon is a small parameter that tells you how big the mode is around frequencies. So if epsilon is large, the width in frequency is also very large. And then it's very sharply peak in a time. So that tells you what is the width in frequencies. And the width in time is inversely proportional to that. And we did the quantization in Minkowski spacetime, and the Unruh effect using plane waves. You can just use wave packets, the same idea, and do it more rigorously. The only thing is that you have to carry away all the time with you this integral, and it's messy. But all what we have done can be done with wave packets, and that is rigorous. And also, this is a basis which is countable. You have infinitely many bases, but it's countable. Therefore, the Hilbert space is what we call separable, and that is what we expect. If you don't know what that word means, doesn't matter. But that is the more rigorous way of doing the question. The second generalization that I want to go relatively quickly over it is the following. Let me talk about energy flux, backscattering, and gray body factors. So we'll have to say it in words. So in this, I want to talk about the approximation that we did. Recall. We made a drastic approximation it was we neglect the potential. So we took the potential that appears on the wave equations and we put it to 0. And that seems to be quite drastic approximation. So what I want to do here is to tell you what happens if the potential is present. So if V is present, we know that modes in the Schwarzschild region must satisfy the following equation. Second derivative with respect to. So I forgot to say that in this section I come back to use the initial out mode. So I'm not going to use wave packet, but I could use wave packet, but let me do it without wave packet. So remember the wave equation. Was this omega L and N? This is the you want the for the out modes, and which is a time independent Schrodinger equation. We neglected the potential, everything was extremely simple, but now we want to include the potential. First of all, recall that the potential was something like this. Potential as a function of R. R is always R, let me put R out. The potential was 0 at the horizon, if this line is the horizon, and then grow, and then went to 0. So the potential is 0 when R out star goes to minus infinity, which is the horizon, and it's also 0 when R out star goes to plus infinity. So what we have to do is one of these Schrodinger problems where we have a potential more here, and we have plane waves here, so part of the wave will be transmitted, part of the wave will be reflected. This is what we have. So now the problem now is more complicated than before, but we, at least theoretically, we know what we have to do. So remember that in our calculations, we were using out modes. We were choosing as out modes which oscillate with positive frequency here. That was our choice. So what I want to start saying is that we can still choose our out modes as such that, because remember that the out modes is our choice. We only need a basis of positive frequency modes there, and there are many. So even if the potential is non-zero, we can still choose modes such that in a square class they behave like this. We can still do that. Therefore, my question for you is that if we can still use modes which are identical as the ones that we did before in a square class, is this potential going to have any effect on Hawking radiation? You understand what I mean? You know, we have the potential, and now I have to make a choice of modes, out modes. I choose the same modes which here, the potential here is 0, modes which behave in the plane. So these modes in a square class are exactly the same as before. So do you think the Hawking radiation is going to be modified?
Maybe for this time back, there will be.
That's the point. Remember that Hawking radiation was obtained computing Bogoliubov coefficients. In order to do that, we have to multiply phi in and phi out, but we have to put them together in a Cauchy hypersurface, because this is what multiplication is, an integral in a Cauchy hypersurface. So what we did was trace back the out modes to square minus. If the potential is there, that back propagation is going to be very different. So this is what is going to change, that the propagation backward in time of these modes is going to be very different if there is potential or there is not. In fact, we put potential to 0 to be able to do that backward propagation easily. Now, we have to really solve that equation and see what the backward propagation is. So, what I want to say is that even though we can make the same choice at the state class, but the propagation backwards in time to sky minus needed to compute the Bogoliubov coefficients is going to be very different. That is the difficulty. And to be fair, to tell the truth, there are no analytical solutions to this equation. Nobody knows analytical solutions to that, so we cannot do it analytically. So the best we can do is to,
So this is what
Anderson. This is what Paul Anderson was complaining about, that doing real computations is difficult because we don't have analytical solutions. So but conceptually we can guess, we can figure it out what is going to be the difference in Hawking radiation. The difference can be huge. The thermal spectrum can go away. Because now the modes are going to be propagated, are going to be something else there. Beta and alpha can be something else, and the thermal spectrum can go away. So was the thermal spectrum artifact of our simplification, or this thermal character still survives? You can imagine that it survives, otherwise you will kill me. The same was, you were here for 3 classes deriving it, and if it is useless. So it survived, but it has some changes. So to figure out what the changes are, we can use our intuition in solving Schrödinger equation. So from experience with a Schrödinger equation, we can guess what is going to happen. I'm going to have here the 2 diagrams, one for the potential, and also this is the potential as a function of R out, and this is the Penrose diagram, the black hole. And I am choosing the out modes. So our out basis is such that very far from the black hole, so R out going to infinity in this region, I am choosing e to the minus I omega u out as the dependency in u out, in addition to all these other factors that I don't write. So here our out modes are just e to the minus I omega u out. It's probably this cannot be seen in the camera, so it's just e to the minus I omega u out, and the same. So what I want to do, this is at infinity, what I want to do is to propagate this backward in time. So I want to do inverse resolution of the Schrödinger equation, but maybe you can help me to complete this picture. In the Schrödinger equation, when we solve this scattering problem, we know that we always have some part coming here, and If we start with a wave with one amplitude, you're going to have something reflected and something transmitted. We are here doing the inverse problem. We start here with something like that, and we have to propagate backwards in time. So we will have something, some component like this with a reflection coefficient. Let me call it R omega, and some part coming here with some transmission coefficient. This is the transmitted part, but I am propagating backwards in time.
Is
And this is consistent.
maybe I'm being silly. When we go backwards in time, is there a reflected wave on the other side going the other direction?
Yes, so let me do it here.
Okay.
Let me see if I understand your question. So let me do the same picture here to see what happens. So here, what we have is some goats moving out, going outgoing wave. And when we propagate it backwards in time, some part is reflected, which means that some part is an incoming wave. Let me change the marker. So we propagate backward in time, some part gets reflected, is incoming with amplitude R L of omega times that, and some part is transmitted. So we have here some outgoing modes with amplitude TL of R, and that will be the complete picture.
Okay, so it's like there's a right moving wave on the right of that bump in the other graph.
Right. So this is outgoing, but in the other side of the potential, you will have a combination of ingoing and outgoing.
Okay.
So it's like if you take this and you propagate backwards in time, some part will bounce the potential, which is this, some part will bounce the potential, and some part will be transmitted.
Why are they perpendicular to the RP?
Should we-
Reflection
Why this
transmitted.
RP is perpendicular to the these rays?
Because this is the incoming direction. This is going towards the black hole,
Okay.
like this. This is decreasing radius. This is propagating towards the black hole, decreasing radius. If I continue, it will fall inside the black hole. So you are going from larger radius, infinity, from here to inside the black hole. And you are decreasing radius this way and increasing radius in that way. So incoming modes, V equal constant, outgoing modes, U equal constant. So these guys also, they are going outwards, increasing radius, so they are coming from here to there. Steven?
That answered my question.
Okay. If you are confused by that inverse scattering problem, you can.
How does that total the part at infinity though? Which there should be three totals, three things in this.
There's 3 arrows in the bump.
Right. This part, and this part.
Oh, that's an arrow that belongs
Oh,
to
that
this.
black arrow is part of the
This
graph?
is part of that.
Whoa, oh, whoa.
I'm sorry.
Okay.
So these are these are two plots. This is the part I start with this and I propagate it backward in time. So one part gets reflected. I'm sorry if I change the color. Sorry. That does it now make sense?
Yes.
Let me add a comment here. On that, maybe this will help you. What I want to add is that if this inverted scattering problem confuses you, what one can do if you want, you can do the following. Okay, that this is what normally you see the problem. What you see the problem is that, okay, I have this around. I'm going to assume that I will start with something which is just purely outgoing, with no coefficient. What I know is that, something will be reflected. Let me call the reflection coefficient depends on L and omega. This is why I add, and something transmitted, which with some transmission coefficient. This is the way that you normally see it in quantum mechanics. But this is equivalent to that. So one can check, in fact, that the two pictures are equivalent, and there is a relation between the transmission coefficients so the same transmission coefficients, they differ in a phase, not the transmission. Transmission are, in fact, equal to each other. The reflected coefficients differ in a phase. That happens to be true. You can check the details in a book of black holes, which is Frolov and Novikov, which is a quite nice book. Frolov and Novikov. It's called black hole physics, and they have all this analysis in full detail. But because I want to have just plane waves in Scray class, I prefer to use that picture. Is that okay with everybody? Now I have a question for you. What is going to be the modification of Hawking radiation?
What's going to be the what?
How the Hawking final result, that particles that, you know.
There is this coefficient that when we go back to I minus, there will be this extra coefficient T. Right?
All the Bogoliubov coefficients will pick up the factor T. Because when those modes are propagated backwards in time, all Bogoliubov coefficients will pick up this factor T squared in time.
And that T squared is very hard to solve for since this problem is
Analytical.
contracted.
Analytical is very hard to solve, but you can compute it numerically. So, what I want to say, I mean, it's just repeating the computation exactly, but just wherever you see an out mode in Scray class, you have to multiply it by that coefficient. And you will see that when you do that, the effects of the potential in the Hawking spectrum is simply, so let me talk about the expectation value in the in vacuum of the out number operator with frequency omega. This is what in the previous computation we said that it is e to the omega h bar Hawking temperature Boltzmann constant minus 1. I write this, but remember that what I really mean is the trace of the density matrix, the Hawking density matrix times the number operator. But just a shorthand, I write that. This is what we obtained before. And also remember that that was equal to the integral omega prime beta omega out square. And remember that beta out was computed as omega prime was computed as the inner product of now I don't remember how I define it. If I put here out or in, it may be the other way around, and there is a minus here. Omega prime here. So I don't remember which way I define beta. If this or the other way around. So take that. But you know, remember this inner product, as I said a minute ago, was an integral evaluated as Scray. We choose to do it at the Scray class. So you know, the only thing we have to do is to put here a TL of omega, and here you have beta square. So the difference is going to be, this is the way that Hawking radiation is going to be modified. So is modified. So remember that this integral in Scray class is an integral in space. So these coefficients go outside of the product if you want. So So each beta picks up a coefficient. You have beta absolute value squared, so you pick it. So the Hawking radiation is modified by that factor. So we cannot say anymore that we have a black body spectrum in a straight line. So Hawking spectrum gets modified. No black body spectrum anymore. What do we have now? A gray. So that we have a gray. This is what people call a gray body spectrum. And the coefficients, these factors, are called the gray body factors.
So are the TL expected to change slowly with omega or rapidly or?
In principle, quite slowly, and they don't, they don't destroy that. Otherwise, we cannot call it gray. We could call it multicolor.
Right.
So it's called grays because you don't modify that much the thermal spectrum. So it's just some modification.
And it's just a function of omega, so it
And L
L.
and omega. Of course, L because the potential depends on L, because the potential, remember, has a centrifugal part. So in fact, the potential goes to infinity when L goes to infinity. We expect these guys go to 0 for very large L. And also, if omega is very large, it doesn't care about the potential, and so this guy is expected to go to 1 for large omega and to 0 for large L. This is why I said at the beginning, in the first section, that the approximation of negating the potential is very good for L equals 0, because the L equals 0 modes doesn't see much potential, because the centrifugal potential is very small. But for large L's, this coefficient, in fact, go to 0. And as we will see in a minute, that is not only reasonable, but is necessary. Is that okay?
Yes. Lambda L corresponds to
lot of angular.
Yeah, lot of angular dependence.
Right. So the spectral harmonic has large L, so large angular momentum. Therefore, the potential, the centrifugal potential, is huge. Remember that BL has all these factors, so the R minus the spatial radius, whatever is here, times L plus 1 over 2R plus another term here. So you have the potential barrier, the centrifugal potential barrier. So that goes to infinity. And as I said, there are no analytical expressions for the gray body factors. There are numerical results. But there are also analytical approximations for very small omega, so compared to the black hole mass. And this one was obtained by Page in Page 1976. And there's also another analytical approximation for very large omega obtained by the Gray DeWitt in 1965, I think. 65. Now just, is that okay? And you can check in books what are these expressions. I mean, they are simple and reasonable. And now just tell you that given, for instance, numerically, those coefficients, if somebody gives you those coefficients, we can estimate the amount of energy per unit time, so the power reaching a Scray class due to Hawking radiation. We have all these particles getting to a Scray class, we can compute the energy. Let me call it pH, power in Hawking radiation. We know what is the number, the expectation value of the number of particles of Hawking quanta. TH Boltzmann constant -1. We know what is the energy of one of each those quanta, H omega. What we have to do is to integrate over all omega and over all L and N, because we have one of these quanta for its value of L and for its value of N. So that would give us a good estimate of what is the energy reaching a Scray class due to Hawking quanta. Of course, we need the value of TL to make this integral. Otherwise it's simple. If TL is equal 1, that is very simple. What happens if TL is equal 1? If TL is equal 1, we find a problem. This is why I said that they are necessary. If TL is equal 1, nothing depends on L. And we have a sum in L that will diverge. So this backscattering, this potential is crucial. Otherwise, we would obtain that the energy carried by particles is infinite. Numerically, you can check that this is of the following order. 2.3 10 to the -4 in units of h bar. So if h bar is equal to 0, there is no Hawking radiation. Pi, the mass of the black hole square, Newton constant square. And this numerical analysis was done for the first time by Elster, 1983, as far as I know. As I said, this power could diverge if TL is equal to 1, because the sum in L diverges.
What is 2.3
times 10 to the -4. Numerically, correct. So people have checked in the same analysis that 90% of the energy of P comes from the L equals 0 mode. So this is why neglecting the potential is kind of a good approximation, because most of the energy comes from the L equals 0. So this is what happens if you include the potential. Now let me take this result to do the following. If I know what is the energy emitted per unit time, and I know that the total energy of my initial spacetime was the mass of the black hole, this energy must be coming from that. So if I know the initial energy and how much energy I am losing per unit time, I can compute what is the duration. I can compute what is the duration of Hawking process. How long it will take for the black hole to evaporate completely. Of course, to compute that, I need to extrapolate this expression for the whole life of the black hole. And that is quite reasonable, except at the very end of the evaporation, where the black hole is of order of the Planck mass. There, this expression shouldn't be trustable. But compared to the whole life, that last instant will be negligible. So I think using this expression provides an excellent approximation to the real world. So by extrapolating this expression pH to the whole evaporation process, which I said is very good approximation, except in the last few Planck seconds, and that is going to be negligible compared to the millions and millions of years that we are going to obtain. We can estimate the duration of the evaporation process. It's very simple. We know that the change of the mass of the black hole per unit time is due to that power. So we have to solve this differential equation. And we know that that is a constant alpha divided by the mass squared. This is what we obtain from here. The power, remember, power inversely proportional to the mass. I didn't emphasize that enough, but that is very important. The power goes as 1 over the mass squared. So the smaller the black hole is, much larger is the power. And this alpha just is obtained from here. Just putting the numbers of h bar and g, I got, if I got right, this alpha was 10 to the minus 76 in units of mass of the sun cubed divided by 7. So the evaporation process first of all
Why is
is
it mass of the sun cubed?
because we need those units here. You know, that has units of you know, this power 1 over time.
Oh,
Yeah.
because it shouldn't be dimensionless, it should be units of mass.
Right, because you have
Okay.
energy over time, so you need mass energy cubed divided by time.
Right, okay.
And I choose to write here solar masses to compare with the solar.
My mistake, yeah.
No,
So
asking questions is never a mistake.
I'm just kind of motivated by our recent discovery when 2 black holes spun and collided each other. Did that extend their lifetimes? If they...
Of course, you know, you get a bigger black hole.
Yeah, of course. Okay, cool.
So can we estimate? Can you guess what is going to be this proportional? You know, you have 1 over mass squared. You can bring mass here. You can bring dt here. The integral is going to give you mass cube. So important result: the life of the black hole proportional to the mass to the cube power. This is the scale of the duration. Now, if we put the constants, I choose that appropriately, and the number that I get here from alpha is 10 to the 68, and it is 68 because I moved this to years. So sorry for changing from seconds to years. I should have here years directly. This is worth 1 second. Pretty large. So if you have a black hole of 3 solar masses, you must be patient. So delta evaporation, you must be patient. Of the order of 10 to the 57 ages of the universe. I think I got it right. It seems still too large for me. And I think I did the right number. Ages of the universe. Seems too large for me.
Do this number make sense?
Maybe I made a mistake in doing something, but you know, wherever it is I'm sure it's much larger than the age of the universe.
It
What I
is
did
possible
instead was 10 to the 57.
10 raised to 60, age of universe is 1 billion, I mean
Is
15
10 to the
billion,
10?
10 billion years.
10 to the 10. It's 13 billion, so it's 10 to the 10. So you know, but you know, this is why this is called, you know,
Yeah, so
you have
it's,
3 solar masses give you a 10 from here.
so it's fine.
But the question is, this number is fine. I believe it's fine. You know, I did it on my computer yesterday, but you know, you can have a typo. So much larger than the age of the universe. Of course, assuming that the black hole is isolated. In our universe, the black holes are still eating the CMB. in the cosmic microwave background, so they are not even start evaporating. So.
Do spinning black holes evaporate faster or slower than short-shield black holes?
Differently. The order of evaporation is quite similar, but they emit particles with angular momentum in a different way because of the angular momentum. But not too different.
Okay.
And but for primordial black holes, and I think the computation is right because I got the right number here, because I knew the answer. For primordial black holes, remember what primordial black holes are. In the very early universe, we have density fluctuations, and they could be large enough to form micro black holes here and there. The estimated mass is of the order, initial mass is of the order of 10 to the 14 grams, so it's quite light. And if you do the computation, the evaporation time is 10 to the 10 genos. And this is why they are so excited, because this is the age of the universe. If they were formed at the onset of the universe, they must be evaporating completely right now.
But then, after CMB was formed, they have been eating.
No, but probably they were hot enough, because the temperature is going to be quite high for these guys. These guys are very light. The temperature is 1 over the mass, so they are going to have high temperature. So the CMB is going to be negligible for them. They are going to be emitting a lot. So if they exist, we should see now at this time final process of evaporation. And as I said last day, that was one of the Hawking ideas. Please go and look for this kind of gamma ray bars or whatever they can be, but nobody has seen them.
They have this new project, right? Hawking and someone, Yuri Miller, and then again, like they are saying this nano spaceship or something like far behind with high speed.
But that is just to go to a different star or something like that.
Oh yeah. So I mean, like using something like that, can we check or something? I mean, like how can one? How can we test like what is T evaporation? I mean, coming from black hole.
No. But we can say if Hawking radiation is right, and if primordial black holes were formed, we should see them in our galaxy, in other galaxies, just evaporating right now, and we don't see them.
Would it have been more likely that primordial black holes just fall into other black holes and keep getting
But the
bigger?
universe is huge, so
I suppose space is big. Yeah.
Okay, so it can happen that what is that called, like Hawking radiation and all everything holds, but I mean, which theory? I mean, that is just model, right? That primordial black hole formation.
Right.
Yeah.
It is possible. I mean, that is what people believe, that the rate of formation of primordial black holes must be very low, if they were formed at all. So this doesn't, the fact that we don't see this doesn't put a question mark on Hawking radiation, but on primordial black holes. That tell us that primordial black holes, if they were formed at all, they were very, very, very real.
It could, I don't know how. So this calculation we did using a scalar field.
Sorry?
We did this calculation using a scalar field.
This is using a scalar field.
The particle that it will be emitted will be
In this
the
calculation,
quanta of that
a scalar field.
scalar.
But you
So
can
for
repeat the
this,
computation.
For radiation or
And you can repeat the computation
fermions.
for photons, for fermions,
Yeah.
and that will emit everything. And you will increase that factor, the power by a numerical factor, depending on how many species you have.
This is far-fetched. So, can these primordial black holes contribute to reheating or something?
Dark matter is what people were using a lot, for instance.
Huh? Dark matter.
Dark matter.
Okay.
And if, because they may be a source of dark matter, but we don't see them in any way. So people have speculated a lot about them, what is the effect of them in galaxy formation, in dark matter, etc.
So that the effect is due to the fact that the light rays pass along the horizon in the diagram effectively. But if the black hole is shrinking, the horizon's going to be shrinking, and it's going to be a curved diagram, kind of, right? So
No, but the event horizon is always timeline. Sorry, null.
the event horizon is always null, even
And-
if it's shrinking?
Right. The event horizon never changes because it's defined in a mathematical way, which is go to the future, take the past of the future, and if there is that has a boundary, that is what we call the black hole. What you have in mind is a more realistic definition of horizon, which people call dynamical horizons. Or
Right, so I'm wondering if anyone has calculated it consistently with a shrinking event horizon.
No, nobody has. If you want, that is a good project.
No, I'd have to actually learn this.
You are doing it right now. Hopefully. Okay, so let's move. I forgot to add another section, but that is too long. And let me just tell you what the conclusion is. The next thing I want to generalize is the model of the process of collapse. We were using a extremely simple model of collapse, which is that the black hole is produced by a single spherical shell coming. So a more realistic is a star or something. Therefore, if we have a star, the propagation backward in time of the modes will be even more difficult. So how Hawking radiation is modified if I have a more realistic model of collapse. I'm going to be very brief here. So independence of the details of collapse, of the collapse. Again, so far we have used a extremely simple and unphysical model of collapse. The black hole is produced by a single shell, infinitely thin, incoming shell of null radiation. What happens if we replace it by something more real, like a star collapsing, like this? Is the final result going to depend crucially of how the black hole is formed? The answer is no. This is why you write dependent. Otherwise, it's like something different. I can tell you quickly what is the physical reason for that Hawking used, and also what is the mathematical reason. At the physical level, Hawking had the following intuition, and he had to think about that because we in our computations we need to take modes in straight class and bring them back to straight minus. If you have a star, in addition to the potential, you have to study how the modes propagate inside of the star, and that is extremely difficult. So that will be even more difficult than the potential.
Okay, so these potentials, right? What are the reasons for this potential?
The mass of the black hole. You have a star. If you want, that is also for a star. You have a star, and there is a gravitational potential. So if you try to go away, the star pulls you. And also, if you decompose your modes in spherical harmonics, you will pick up a centrifugal potential. So the two reasons: the mass of the star pulling back, and the gravitational potential, and the centrifugal potential. So that is very difficult. So Hawking had the following idea, physical idea, which I think is very nice, and it works. He said, okay, as we just said, we have to take here an out mode with some frequency of the order of the mass of the black hole, because this is what Hawking radiation tells us, and we have to propagate it backward. And I am interested in late time modes, so modes that go in the past reach very close to the horizon. As we discussed that, because of that potential, there is a blue shift when we go backwards in time. If you see some mode here of Hawking radiation, when you propagate it backward in time, here we have a frequency which is exponentially large. So the exponential factor time omega. So those modes here will have a frequency exponentially large. But first of all, please don't think about real modes going. These are not real particles. These are just these basis modes that we are using. They are not. But this is what we need to do mathematically, propagate the backward in time. And Hawking said, if a mode with an energy arbitrarily large tries to cross the star, doesn't care about the star because it's so energetic that the star is essentially transparent for it. The propagation here is trivial. The mode is so energetic that the details of the star are completely negligible for them. The wavelength is so short that, if this is an atom, the wavelength is so short that it will don't see the atom.
I mean, why can't we like use this star as like add to the potential which we have?
That is even more difficult because you have to model a star and you have to solve the wave for propagation. So it is already difficult to compute it numerically without the star. With the star, it goes beyond anything. And in fact, if it's a photon, the photon will interact with the star, and that is extremely complicated. But if the photon has an arbitrary large energy, the star is transparent for it. Doesn't interact.
So in the omega basis, we can't choose omega arbitrarily at the horizon. But in the J and T basis, we can choose J arbitrarily
No,
near
so
the horizon.
we choose modes in a scale class, the ones that we care about, the ones which are around Hawking peak, which is of the order of the mass of the black hole. These are the modes that we are going to see in Hawking radiation, and we propagate it backwards in time.
Okay,
So,
so there's both a peak in omega and in the position
right, the
along.
and we only care about modes which are here at late times. Remember that Hawking radiation only happens for late time modes, and these are the ones that when you propagate backwards in time, they go arbitrarily close to the horizon. So Hawking used what he calls geometric optics approximation. Which means just that when you have waves with arbitrarily large frequency, they just behave as a kind of particle, and the propagation is insensitive to the details of the star. So this is what Hawking did. Mathematically, what happens is the following. Let me just summarize it quickly. Remember that in order to compute our Hawking radiation, one of the mathematical key features was the relation between the U in and U out coordinate, and I have emphasized that several times.
So how can they behave as a particle when there are no particles at the horizon?
No, it's just the propagation of the wave. It's just a mathematical
okay.
part. You have a wave equation, and when the wavelength is much shorter than any other scale, you can approximate the evolution as a ray. This is the standard.
As a ray.
As a ray.
Okay.
Not as a particle, as a ray, I can say. I mean, sorry if I go fast, but otherwise we are going to be super class.
Sorry.
No, that's fine. That's fine. So remember that this is the relation between in and out coordinates that I use, and I emphasize that this log is responsible for Hawking effect. So one can show that if you complicate the star wherever you want, I mean, this expression was for this simple case. One can do the exercise of having two null shells to see what happens with that relation. And what happens is that you pick a numerical factor here. You can have 3, and this factor will change. You can have a star, and this factor will change. But the logarithmic relation is exactly the same, and the Hawking radiation at late times doesn't depend on this factor. It's completely insensitive to this factor. So at late times, because you can always use the logarithm to change this by something proportional to the logarithm of c. And when at late times this is huge, so this is going to be negligible. This is going to be negligible. So let me say it again. The details of the collapse of the star is going to give me here some coefficient, and you can see that just doing models with increasing level of complication, that like having 2 rays, 3 rays, 5 rays, all what changes is that c, and that c, because it's a log, you can add or subtract something like proportional to the log of c. And at late times, which is when Hawking radiation happens, at late times mean that U in is very close to VH, so this is close to 0, the logarithm dominates, and all these other factors are negligible. So the statement here is that late time Hawking radiation is independent of the details of the collapse. Of the collapse. And I think it's a very nice exercise to do that, you know, to see that explicitly, taking, for instance, a model in which rather than one spherical shell collapsing, you have two. And you can see how that changes explicitly. And if you want to see the computations, there is a nice book on that. It's called Fabry and Navarro Salas. They have that in detail. It's called Modeling Black Hole Evaporation, and you can see that example done in detail. So that is a very nice feature of Hawking radiation. That all the complications of the star, how the black hole forms, are unimportant for Hawking radiation of late times. So this simple model that we use really captures the essential ingredients of Hawking radiation. Is that okay with everybody?
So why is the stellar surface model as a curved?
Is what?
Stellar surface? Why is it
Curve? Because remember that a Penrose diagram is made in such a way that
light rays are
at 45 degrees, the price to pay is that
anything else?
anything else is the form. So, you know.
And
Remember I explained that, you know, any time-like curve must begin there and must end here or at the singularity. So this one was there. So this is the interior of the star. The metric there is not Schwarzschild, it's something else. Depending on the star. But the statement is that Hawking radiation at very late time is independent of the collapse. Those details become negligible. Only this log is what produces the Hawking radiation mathematically. Physically, you can think about
so what you are saying is that if you have more shells, the Schwarzschild radius will change.
Schwarzschild radius will change. Of course, final mass will change and the temperature will change, but the spectrum will be thermal.
So and any change in the Schwarzschild radius can be taken out as a factor.
Exactly, and final, you know, the Hawking temperature will be different, but all the rest will be exactly the same. This is what I proved. Sorry if I am fast on this. So now I want to go to the last section. I wanted to finish today, but it's going to be possible. I want to discuss, to finish this chapter, section 4, some consequences of Hawking radiation. And as we discussed last day, and you know, Hawking radiation is a really profound result in many sense. You know, just look at the formula, you have h bar, so quantum mechanics, g, gravity, Boltzmann constant, the speed of light. So it's a really rich result connecting many different branches of physics, which a priori were not related at all. So you know, the consequences are huge, and most of them are they still need to be understood. We don't understand them well enough. So I'm going to summarize two of them. One which I believe that there is consensus, and the other one which is completely open. The first one is just closing this black hole thermodynamics analogy, which is, you already know what the answer is. Black hole thermodynamics and Hawking radiation. And the other one is the information loss paradox. I will describe this one today, which is short, and we can discuss the other one next day. The only thing is that the information loss paradox is a field by itself. We could have a whole course on that, so I will just show you a summary of the main ideas of the market and even my viewpoint. So here, we can go fast because you already know the answer. So the argument is that we have to recall the main impediment in bringing the analogy between the black hole, or the loss of black hole mechanics, and the ordinary laws of thermodynamics. The main impediment in making this a physical analogy was that temperature of a black hole in GR is exactly 0. So remember that there were three quantities. Energy seemed to be related with the mass of the black hole, and that's it for a very reasonable analogy. The entropy seemed to be related with the area of the black hole, and all these arguments by Bekenstein about the generalized equal law seem to be reasonable. But the fact that the temperature of the black hole is related to the surface gravity seems completely wrong from a classical viewpoint. From a classical viewpoint, GR tells you that black hole is a perfect absorber, and it's nothing, temperature 0. Any reasonable definition of temperature is absolutely 0. So that analogy, that physical analogy, could not stand in the classical theory. But now everything changes. Hawking tells us that if quantum mechanics enters into the game, black hole radiate as hot bodies with a physical temperature which is proportional to the surface gravity, exactly what the analogy required for us. Proportional to the surface gravity, precisely as required by the analogy. Remember that the analogy suggested that temperature should be proportional to kappa, the surface gravity. Remember that the surface gravity is just 1/4 times the mass of the black hole, times g to have appropriate units. And we had an alpha there, and that alpha also appeared in the entropy. Because we had to divide the constant between the alpha, the temperature and entropy. So the entropy was area divided by alpha. But now Hawking tells us not only that the temperature exists and is physical, but also tells us what is the value of that constant. I don't have it today, but we have written it before. H bar divided by Boltzmann constant, the mass of the black hole. Sorry, no, not the mass of the black hole. I need to see the factors.
8 pi z kb and
A in the denominator.
yeah, above is below.
8 pi
z kb and
z.
yeah, z. I mean gravitational constant.
G.
Yeah,
kb.
yeah, kb and b. Mass of black hole.
Oh, no, but it's already in kappa, so we don't have Q.
Oh, okay. Yeah.
So in other words,
So we won't have z.
we don't have G. In other words, alpha is 4 h bar g over Boltzmann constant. I have that. So in summary, Hawking result strongly indicates that the laws of black hole mechanics are nothing else but the physical laws of thermodynamics applied to black hole. And that is an extremely strong statement. You know that these theorems that were derived in general relativity, geometric theorems, they are just the result of applying the standard rules of thermodynamics to a black hole system. So therefore, the laws of black hole mechanics, they are just the thermodynamics applied to black holes, and that is completely astonishing. Remember this idea that that the black hole, the laws of black hole of thermodynamics, they are just macroscopic averages over a lot of degrees of freedom, and they are based on probabilities on statistical mechanics. So they have nothing to do with theorems in GR, which are precise theorems in differential geometry. It happens that they are physically the same. Oh, that is completely unexpected.
So like instead of thermodynamics, we should say statistical mechanics.
But thermodynamics is kind of the macroscopic version of the statistical mechanics.
Yeah, but
And
here
it's-
like we deal with statistical mechanics, right? I mean like thermal state and all.
But that is just we just define a temperature and an entropy. We don't know what are the microscopic degrees of freedom producing the black hole entropy or the black hole temperature. So we are really at this level. This is just thermodynamics. We see an entropy, we see a temperature, and so in particular, with alpha, we have the entropy of the black hole. Remember that was A over alpha in the analogy. So now that we have alpha, the entropy of a black hole is given by the area for hg. And if you let me add the speed of light for a second, which normally is equal to n, then you can check that this is precisely the same as area over 4, and these constants are just the Planck length square. The Planck length is just root square of hg over ct. And this is the celebrated Bekenstein-Hawking entropy. It was proposed by Bekenstein that it had to be proportional to A, but was Hawking result which provides the constants here. So this is why it has the two names. And this completely closes the analogy. We now have the generalized second law that we discussed due to Bekenstein that tell us that if you have a black hole and you have matter, the sum of the entropies of matter and black hole will always increase with time. The black hole entropy can decrease emitting Hawking radiation, but you are increasing the entropy outside, and if you consider total entropy, entropy always increases. So this is the generalized second law, which is the standard second law generalized to systems, including black holes. A good question is how big is this entropy?
What's SN again?
Sorry?
What was SN again? The
I
S-
don't
This is
know.
the entropy of matter, or the standard matter of the black hole. For instance, of Hawking radiation. For a black hole of 3 solar masses, you can put the numbers there, and the black hole and the Bekenstein-Hawking entropy is of the order of 10 to the 78 times the Boltzmann constant. which is around 20 orders of magnitude larger than the entropy of a star with the same mass. So the entropy of a black hole is ridiculously large, extremely large compared to any other system, like a star. You know.
So a star of 3 solar masses collapses into a black hole. Where does the extra entropy come from?
Entropy increases in the process. If I throw this to the floor, the entropy increases. You take an encyclopedia and you burn it.
Okay, so it's not adiabatic at all.
Right,
It's
it's not
just-
adiabatic at all. You are generating a lot of entropy in the collapsing process. But it is curious because the black hole, as Chandrasekhar defined it as the more pure system, because it's pure gravity. The black hole, there is nothing else but gravity. Exactly. You have the singularity there, but and that has a huge entropy. And the entropy is proportional to the area. Why not the volume? Why the area?
And if you, sorry.
I just, well, it's a question, maybe stretching the analogy too far, but if entropy can be thought of as log of number of microstates, what am I thinking about the microstates?
I'm going to discuss that.
Okay.
Just one minute.
So another mystery is that, and these holographic ideas that, that all the information in a volume can be codified in a surface, this has stimulated a lot of ideas about holography and all that stuff. So why area and not volume? And second, as we were discussing, this huge number of microstates. We know that this has something to do with quantum mechanics because Hawking radiation only arises when you put at least a quantum field. So it is quite. I have little doubt that the degrees of freedom, the microscopic degrees of freedom, the statistical mechanics behind this must be quantum gravity. So black hole is made only of gravity. There is nothing else inside a black hole. All the matter went to the singularity and is lost. So black hole is pure gravity. So this entropy has to be gravitational degrees of freedom, and we expect that quantum gravity is going to tell us what the number is coming from. And all the big proposals, the candidate theories for quantum gravity, they have focused on that. String theory, they have focused on obtaining Beckett-Hawking entropy. Loop quantum gravity has focused on that. So they have
If you don't have a singularity inside just the horizon, you still have these results?
What people have done in loop quantum gravity, for instance, is quantizing the horizon and doing the quantum geometry of the horizon. Thinking about the horizon as a quantum geometry, and you can build the Hilbert space and you can count how many degrees of freedom it has, and that counting produces something which is proportional to the area, and so it's compatible with that.
But my question is that does it have essentially something to do with having a singularity at the center, or is just
No.
just the
Normally,
horizon?
in those computations, either in loop quantum gravity and in string theory, the singularity doesn't play a role for that. Because I believe that this entropy has not nice to do with singularities more than quantum geometry itself. Because we are obtaining here without.
But classically, also, if we just have a horizon,
So
so
that-
if we did the calculation
for a horizon with a singularity, and you will obtain that. So in loop quantum gravity and in string theory, you do these computations without caring about the singularity, and in string theory, you obtain exactly that. In loop quantum gravity, there is the Barbero-Mircea parameter, that there is a value that gives you 1/4. So any self-respectable quantum theory of gravity have tried to do this computation, and they only call them respectable if they obtain something proportional to the area, and that has happened in string theory, that has happened in loop quantum gravity, and in many other approaches. In so many approaches that people have wondered why everybody gets the right result. Why all these very different theories are obtaining the right result. And that has stimulated people like Steve Carlin to believe that there is some kind of symmetry producing that. And they believe conformal symmetry close to the horizon, maybe behind of this universality. But that is a different history. So here, the lesson to learn is that there is an entropy, there are microscopic degrees of freedom, and we believe they are quantum gravitational in nature. So this really opens the window to study the statistical mechanics of black holes and quantum gravity. So you can see the amount of physics that Hawking radiation is connected. It's really impressive. Next day, I will discuss the information loss paradox briefly. I imagine that you already guess what is going to be, what is the problem, and I will discuss it briefly, and it will start next chapter.
So you have quantum gravity theories trying to get rid of similarities, but there's no theory trying to get rid of the horizon itself.
No, because the horizon, as we discussed, may happen even in this room. We may have an event horizon here. So I would never accept that quantum gravity has nothing to do with the geometry of the horizon. The curvature of the horizon may be
But what does that mean?
arbitrarily low.
What does that mean to say that you have a horizon in this room?
If you try to escape to infinity, you will never reach infinity. This is the definition of an event horizon.
It's not that you have to cross the horizon.
No.
That's
Remember that
you
in
always-
our model, we had a horizon in Minkowski spacetime with zero curvature. If you have a now shell of radiation collapsing, the spacetime is Minkowski in this region, is Schwarzschild in this region, the Minkowski in the entire region. This is an event horizon, because whatever happens inside will never escape to infinity. And here the curvature is zero. Exactly zero. And you have an event horizon. Because a shell will collapse in a few weeks. So you may have a horizon now here because something will happen in a billion years. In such a way that if you try to run now as fast as you can, you will never escape to infinity because of that collapse. So it's already too late to escape to infinity. But the curvature of a Schwarzschild black hole is inversely proportional to the mass. So the bigger is the black hole, the smaller is the curvature, and with some powers. So you can make the curvature of the horizon as small as you want, even zero in this kind of artificial models. But in a real black hole, you may have the black hole and you cannot even notice it. This idea that the black hole, the horizon, is going to destroy you, that is.
I forget if you have a collapsing star as opposed to the ideal picture of infinitely small radiation collapsing in. Do we have Minkowski, Schwarzschild?
No, because in that case, right, you have the star, and the metric inside the star is whatever it is inside the star. So that only happens in that simple model. But what I say that even in a real star, if the bigger is the mass, the smaller is the curvature of the horizon. And you can make the curvature of the horizon as small as you want, just putting more mass. So believing that quantum gravity has something to do with the horizon physics, I think is not, it's a modification of all our ideas. And believing the horizon is any spatial surface, in my opinion, is in conflict with any of the ideas that we have in GR. So all these firewalls scenarios, they say that something dramatically happened at the horizon, and the criticism normally is that is a drastic modification of GR and quantum field theory. Believe that something dramatic is going to happen at the event horizon.
Yesterday we were confused about this. The model that we have taken, we have this line where we have Minkowski coordinates and we have Schwarzschild coordinates. But I was saying that the space is flat everywhere. So space is Minkowski, we're just using different coordinates.
Where is Minkowski?
That's not, yeah, I don't think so.
It's only Minkowski before
Right. So
Before
if this is what is
the radiation
here,
becomes
this is a collapsing shell that is going to collapse at this time. Let me call this V naught. So here the space-time is Minkowski because that shell is outside you, and applying the Birkhoff's theorem, the curvature here only depends on what happens inside, and we don't feel that. So here curvature 0 Minkowski. But as soon as this shell collapses, what you have is a Schwarzschild geometry with some mass.
So when the shell's infinitely far away, it's flat. But
Right.
then when it's less than infinitely far away, it
No.
is.
No, it's
No.
still flat inside.
Right.
It's flat inside.
Right. So inside that is
shell.
it's flat, but after
Yeah, after it passes you,
Of the
right,
black
say.
hole.
that is Schwarzschild.
Okay.
You have a mass of the black hole. You have curvature. You have otherwise you cannot produce a singularity. You know, it's not at all a coordinate effect. You know, the geometry here is Schwarzschild. You have a mass, which is the mass that has collapsed, is the energy that comes to you, and here the curvature is 0. Here is not 0. Of course, this is very artificial. What you have to imagine is a star, which is collapsing and forms a black hole. And inside the star, the metric is whatever it is. Outside is Schwarzschild geometry. Here, again, flat metric, Schwarzschild geometry with curvature, with gravity.
So if half of the horizon is in that in different geometry and half in the other.
Exactly. So in a region of Minkowski system, you have horizon. And I was insisting that. Please think about that because it's highly non-trivial. That tells you how artificial is the notion, how teleological. You know, teleological means that something that depends on the whole history of space-time. You need to know the whole history to tell me what happens there. There is here horizon because in a billion years a black hole will be formed in the solar system.
So that's we have defined it in such a way like a boundary which cannot be crossed. So
Exactly.
it may depend on any future.
Exactly.
So that depends on how.
But
we
that is the
define
definition
it.
of event horizon. So many people, including myself, believe that is not a physical definition. That what you have to define is some kind of quasi-local notion of horizon. These trapped surfaces that you form in a collapse, and they are called dynamical horizons, or they are much more physical than these teleological event horizons. But you know, many people believe that, and in particular, all this program of isolated and dynamical horizons that Ashtekar developed is known for 15 or more years. And it's quite clear that, I mean, my opinion, that is what one should think about talking about horizons.
And those are GR papers.
These are classical papers, GR papers.
No. Now when we
It's
have
just defining horizons in a quasi-local way. You don't need to read the whole history of the space-time.
Okay, so backing up to something you said at the beginning of the lecture.
I have to leave.
Oh, I'm sorry.
That's
You said something about this transplanckian effect thing, where when the light's passing by the horizon, it depends on.
But remember, they are not real light. This is just the mode function that we are just propagating over now.
Okay, but the fact that the mode function passes by the
Right.
horizon means that it might depend on the Planck scale, but then there's this other resolution that you discussed later in the lecture. Or at least I think that's what you were talking about.
Right. I didn't tell you what the argument is that people have done many. I don't think it is 100% solved. That that nobody has shown once for all in a theorem that Hawking radiation doesn't depend on arbitrarily high energy.
Okay, but what I was wondering
But people
is,
believe strongly that.
the fact that the quasi-normal modes have been detected by LIGO, doesn't that test the fact that the horizon's not Planck scale?
Not necessarily, because the picture is different. You know, these modes were not emitted arbitrarily close to the horizon. So that radiation was not emitted arbitrarily close to the horizon. So I mean, it's a good point, but I don't think that is tested then.
Okay, I don't know enough about the details to know. Okay, thanks.
My answer is that I don't think that is tested.